then we'll finish it up tomorrow. So I'm going to try to just stay right into it. I went and looked last night, and I tried to come up with a great reason for why.
You're digressing.
This is class material, not digressing. I got you. But why, other than just saying it has to be that way, why do pseudo-unipolar neurons have to be the trigger zone out there at the end? I still didn't have one any better than what I said when I said, well, what's your religious beliefs or non-religious beliefs? What I meant by that always is, we don't know. Who do you believe designed it kind of thing? You know what I mean? I wasn't trying to bring religion into it. I was trying to say, I may never know the answer to that question, but it makes sense because it got all into, y'all can all not listen to this, I'm just talking it's things that I've never even gotten into, like where it transitions from chemical gated channels to voltage gated channels is right at the trigger zone of all these neurons. And then when it round about, I read all this and it comes back and says, well, in pseudo-unipolar, they're out at the end, basically. And I'm like, that's layman's terms. Well, we already said that, I'm trying to get more. But, I'm not going to keep going. I was trying to get you something more, but it just wasn't just the way it is. I don't know. Why aren't ears on the side of her head? I don't know. Just made that. Okay, neuroglia. We were talking about neurons and structural classifications, and then the rest of the cells that surround, like your cerebral things in your central nervous system, peripheral nervous system, are neuroglia, supporting cells. So we need to talk about the different types of supporting cells. One of the problems with neuroglia is if you are to damage neurons, you'll just have more neuroglia form. Because neurons in block 2's material do not go through mitosis. You're not going to make new neurons in your cerebrum. I say in block 2 because when we get further on, when we get to like special senses, we're going to see there's one place in the body that neurons are replaced, and that's very, very, very unique, and that's your olfactory neurons. Your olfactory neurons can actually replace themselves, but all other neurons in the body, you kill them off, they're not coming back. But it smells different. But for now, neurons are not replaced. All right, you just get more neuroglia. I keep saying that because that comes with problems. Okay, so here are the neuroglia of the central nervous system. Yeah, funny names. Astrocytes, my favorite here, oligodendrocytes, microglia, epinemal cells. Those are all central nervous system. And in the peripheral nervous system, we're going to have two. That's going to be our Schwann cells and then satellite cells. So I kind of just left them in the chart. Though if you go into the book, I know a lot of y'all don't even get into it, but if you were to get into the electronic book, you would see that there's different stuff written beside these. I didn't like the way it read, so I added my own to kind of simplify, maybe not the first one, but the next couple I did. Main things about these astrocytes are, yes, they're helping. When it says regulate the composition of extracellular fluid in the central nervous system, we're talking about like CSF, cerebrospinal fluid, which is a very specific type of fluid. So really what we're learning here is astrocytes make up part of the blood-brain barrier. I'm not so concerned about influencing neural synapses because they may do that. You'll notice that I don't ask a lot of things when it says it may do that, because how do you define that? Well, the main thing, astrocytes are part of the blood-brain barrier. When you look at oligodendrocytes, they're going to myelinate axons in the central nervous system. So we're going to have myelination of neurons in the central nervous system and the peripheral. And all you need to know about these is in the central nervous system, the job of that is oligodendrocytes. And then microglia goes back to talking about macrophages, right? Microglia are macrophages in the central nervous system. So they're phagocytes of the central nervous system. Clean things up, keep it clean. And then the last one in the central is epinemal cells. These are very, very important cells. We're going to see as we look more at the neuro side that when you look at capillaries of the brain, they are surrounded, they have a layer, their epithelial cell layers are ependymal cells, and they're actually very, very selective for what gets out of the blood that goes to the brain into the cerebrospinal fluid. So really, we're going to learn that ependymal cells have very tight junctions. Y'all heard of the blood-brain barrier. Things don't get into CSF because of the tight junctions. Well, you're going to have astrocytes that are surrounding these that do some of the work, but the main job of the blood-brain barrier is ependymal cells, because anything that gets into or out of the blood or the capillaries to the brain into the CSF fluid has to go through an ependymal cell. So it can select what it wants to let through, and it's very selective. Like things like antibiotics, which we would hope would get through, do not. Not a whole lot does. Okay. We're switching here, there's a line, so that's peripheral nervous system below here. We have two, we have Schwann cells, which myelinate axons in the peripheral nervous system, and then we have satellite cells, which are just another support cell that we find surrounding these neurons in the peripheral nervous system. They're going to help regulate or exchange material between neurons. So we spend a lot of time talking more about Schwann cells than we do other things, ependymal cells. So we're going to break a few of these down. When you look at a Schwann cell, or a neuroglial cell in the peripheral nervous system, and including satellite cells are going to be kind of over the cell bodies of neurons. So the cell bodies in the peripheral nervous system have these satellite cells, and so it helps to do exchange of materials. A Schwann cell is actually going to wrap itself around an axon and myelinate it, which is going to be an interesting talk as we go through it. We're going to get to that in just a second. I already said this, neurons do not go through mitosis, so they kill them, they're dead, you huff paint, they're gone, right? You're stuck that way. Neuroglial cells do it, and I said that would become important because any cell that goes through mitosis runs the risk of genetic problems, right? You have a problem with the DNA in it, or it's messed up. You can develop tumors and things. Well, same thing happens with neuroglial cells. Because they can go through mitosis, you can get things like, and they have some really cool names here. I love this, oligodendrogliomas. I wouldn't want to have that. Astrocytomas, schwannomas. So when you say you have like a brain tumor, it's not your neurons, it's the supporting cells, the neuroglial cells. All right. In the peripheral nervous system, Schwann cells myelinate axons. In the central nervous system, the oligodendrocytes do that, but they do it in kind of two different ways. So myelin is just a complex of lipids that surround an axon. But really what's happening is, what is the part of the plasma membrane is the lipid bilayer. So what's going to happen is these cells are going to wrap Schwann cells are going to wrap their plasmolemma around an axon. So you have multiple layers of lipids, and they call this a myelin sheath or layer. Like myelin is like coating wires. If you have a bare wire that goes from here to the PX, the signal's not going to travel very far, electrical wires. And if they were to put a coating on it, insulation, it would help to preserve that signal, right? Electrical wires. Myelin's doing the same thing. So it preserves loss of the electrical signal in the body, and it also speeds it up. Right? So it's going to be much faster if it's a myelinated axon. And then a Schwann cell. This is a little bit confusing. A Schwann cell also has another name, neurolimocyte. This is the part you got to kind of catch on. It flips in your brain. Because if you say neurolimocyte, that means that you have a Schwann cell that has wrapped its plasmolemma around an axon. not all Schwann cells wrap their plasmalemma around the axon. Right, so I'm going to show you the difference in how it does it and why we would call it a neurolemmacyte versus a Schwann cell. Where it's confusing for people is they go, well, a neurolemmacyte is a Schwann cell. It is. But a neurolemmacyte is a specific name for a Schwann cell that's wrapped itself around, because not all of them do it. I know I just said the same thing twice, but I'm trying to get that point across. Okay. So I'm going to show you what it does. So Schwann cells myelinate segments of axons. As it wraps its plasmalemma around that axon, the nucleus of that Schwann cell is going to get pushed to the outermost layer. And so the outermost nucleated layer of a Schwann cell that is wrapped around an axon is called the neurolemma. So they gave that a name. That's why when they could see that, now they call it a neurolemmacyte. What I said just a second ago, you can have axons that are associated or have Schwann cells associated with them that do not wrap around the axon, and in that case, they're considered unmyelinated. You know I'm known for my fancy graphics, so I got another one for you. This is how a Schwann cell myelinates around an axon. The axon being in the middle, watch the nucleus as it gets pushed out. And so it's wrapping its plasmalemma around that axon in little segments. So once that completes, now we would call this a neurolemmacyte. And that's the name for that process. They say, well, it has a myelin sheath now. They've coated that axon in that myelin. I don't think you'll need to watch that again. At this point, let's do it. When it looks like this, would you say that axon is myelinated based on what I just said last slide? Is that myelinated or unmyelinated? Right now it's unmyelinated. Just a Schwann cell associated with an axon. Now it's going to wind up myelinated at that point. So at this point you say neurolemmacyte. Yes? That was Louis. That was it. Yeah. I'm going to show you another picture of that. Right here. So over here we have unmyelinated axon. This is a Schwann cell. Alright, so pinkish there. And these are all axons that are close to it, right? But they're not wrapped around, so they're considered unmyelinated axons. But all of the four pictures on the right side of the screen are showing that you start wrapping it around, and then ultimately you wind up with a complete neurolemma where the nucleus has been pushed to the side. Yes?
Does the unmyelinated sitting inside that Schwann cell still preserve some of its ability to send the signal? Or not really?
Somebody's asked me that before. They're saying, I don't know if y'all heard that, he's saying, if you have an axon that has no Schwann cell associated with it at all, we know that's unmyelinated. So the question, the way I'm rephrasing is, well, would this be faster conduction or more insulated than an axon that doesn't have it at all? And I would say yes from what I've read. But it's still going to be slower than this. Because we're going to see there's a purpose to this. Okay, so a few things we got to see and understand is that Schwann cells myelinate these axons in the peripheral nervous system, but they do it in segments. So this is one neurolemmacyte. Here's another neurolemmacyte. So it does it in like little 1 millimeter or smaller segments. Right? Size doesn't matter there. And so the outer layer, that neurolemmal layer, is going to contain most of the cytoplasm. The nucleus sits out there. Remember back to when we started talking about neurons, yesterday we didn't talk about a neuron having this layer. So what is the outer membrane layer of a neuron called? I know it's on the slide, just the way you talk. Axolemma. Sarcolemma, axolemma. So an axolemma is the outside of this neuron. So where would the axolemma be? That would be here. Got to use this that's your axon, and so on the outsides of your axon, you have an axolema that goes all the way along it. A neurolema layer would be here. We only see this in the peripheral nervous system. You got the difference, axolema, neurolema. If you had an unmyelinated axon, you would never have a neurolema, right? One of the key things about these is when you see these segments, in between them, you're going to notice that on these myelinated axons, you're going to see between them, there is a dilated area that's in between each segment. And those are called nodes of Rambier. They fill in the gap area between the segments that are myelinated. Now we find nodes of Rambier in both the CNS and peripheral nervous system, but we only find nodes of Rambier in axons that are myelinated. For once, I'm not giving you pieces of the future story. I'm just telling you the way it is. We're going to come back to that. I'm going to show you later what the nodes are for and why all that matters. When we looked at a muscle cell setup, I gave you one slide here to show you that nerve nomenclature for the sheaths that surround them are pretty consistent with how we looked at it in muscle. We're going to go from the smallest here. We have an axon, and then we have myelin. So I guess I didn't say that earlier, all of the Schwann cells myelinate segments. All of those together, myelinated, means you have a myelin sheath around that axon. So the myelin sheath would be there, and then you would have your endoneurium, right, inside neurium. And then surrounding that, you would have your perineurium. So perineurium surrounding the fascicle. And then the epineurium is going to surround the entire thing. All right, so the Schwann cell is not out here, right? It's right here on each individual axon. So each one of these would be axons surrounded by myelin. You need to have a collective covering. Okay. If you didn't get that, that's because what is a collection of neuronal axons in the peripheral nervous system called? Nerve. There's many, right? We do it as one all the time, but there's many. So a collection of neuronal axons in the peripheral nervous system is a nerve. A collection of neuronal axons in the central nervous system is a tract. Right? Just, we got to look at myelination also in the central nervous system, but just briefly. Oligodendrocytes do wrap around and myelinate similar to a Schwann cell, except for they do not do it segment by segment. There's no neurolema, so it's an astrocyte just wraps its plasmolema around and it has many extensions. So I kind of picture like an astrocyte hanging out, and it can reach out and touch different neurons, right? If we were to draw more on here and say, well, here's, sorry, I said astrocyte, didn't I? Oligodendrocyte. Did I say that many times? I didn't mean to confuse you. Oligodendrocyte's myelinating it. So here's an oligodendrocyte. Here's an axon, and it has extensions that will go out and myelinate. It doesn't make a neurolema because the nucleus is still back in here in the cell body. If we drew another neuron out here and another neuron axon out there, it could go out and grab on. Same thing. It's like it's hanging out in there, right? He grabbing onto different neurons. I don't know why it does it that way, but that's the way it does it. So you'll have many oligodendrocytes myelinating things. There are nodes of Rambier though. They're important, building up to that, but they're important for transduction of, or conduction of neural signals.
So you could wrap around a bunch of times,
Yes. Each segment of an oligodendrocyte that grabs on will wrap out. Picture I'm the oligodendrocyte, and each of my hands grabs two different neurons. The heart or the nucleus is still here in the cell in that case, but there won't be an outer nucleate layer, won't be a neural inside or anything. It'll just be where it caught onto. Alright, so now that we know what myelin is, white matter that you've heard about in the cerebrum, in the spinal cord, the white matter is myelinated tracts, because when you look at myelin on these nerves, it appears white. When you look at the gray matter, the reason it's gray is the mesal bodies. Prominent clusters of rough ER inside of a neuron cell body give it a gray appearance. And when you have a whole collection of neuronal axons together, it'll appear gray. So you have areas of the central nervous system that are considered gray areas. We have white areas, and it looks like this. In the spinal cord, it's going to look kind of like an H or a butterfly. It's all your gray. Human matter is there, where you have all the cell bodies. And all of the white that we see out here is the tracts, myelinated tracts. Same thing over here. All of the neuron cell bodies in the cerebral cortex lie out here in the gray matter, but their myelinated axons are the white matter tracts. And there is some interspersed, right? Meaning there are some areas that have a mixture of gray and white, but for the most part it's separated out this way. Alright, so this is where we tie that all back together. We have to get through that so we can get here.
Is the white matter typically associated with central nervous system, and the gray matter is typically associated with the peripheral?
No. I mean, it's a good question, but no. He said, is the white matter associated with central and gray matter with peripheral? That's what you said, right?
Yes.
No. Just picture the brain. You have gray and white matter. So the gray matter would be the neurons, cell bodies. But they got to get info to them and out of them, right? The neurons got to make decisions. They do that using tracts, and the tracts are myelinated. So that's the white matter. So you're actually going to have gray and white matter in the central and peripheral nervous system. But the spinal cord and the cerebrum is all condensed and packed in together. Does that make sense? There's not really an area we can cut through and look at like we can in the peripheral nervous system, like we can in the central. But there's gray and white in both. Alright, so we're going to switch and talk now about what are these signals you keep talking about. We're actually going to start to learn what action potentials are. So every cell in the body has a membrane potential, meaning the plasma membrane. What is its potential? The potential is looking at the charges that are on that membrane, the difference in voltage from inside and outside of that membrane. Nerve cells do this even more because they're very specifically adapted to make changes in membrane potentials. When we change the membrane potential in a nerve, we not only can depolarize one area of that nerve, we can actually use the nerve to transmit that signal. We can send a signal out. What I'm trying to say there is, like a muscle cell membrane can be depolarized and cause an action. Any membrane can. But the nerves can carry that signal where it needs to go. Okay, so we're going to look at how a nerve conducts electrical flow to send nerve impulses. Alright, we got to talk about communication. I've used this word and now we're going to learn it as action potentials. Nerve impulses are action potentials. We either need to communicate close or far away. Right? It's either local or right, all or none. Right? Action potentials are always all or none. All that means that we need to think of is if I had an axon that was from here to the IPAP offices over there, it was that long, and I started an action potential right here, it would travel the length of that axon at the same amplitude all the way down. Once you initiate it, it's all or nothing. It's going all the way to the end of that neuron, or axon. It is the end of the neuron, it's the axon. Right? So that's a very all or none versus graded potentials. Graded potentials are short distances. They generally travel like from one neuron to the next. And so we're going to have a graded potential that can make changes in other neurons. Right? That's not an all or none. I have to show you a picture to draw that out here in a second. But just for now, graded potentials are short distance. They're called localized. They're not all or none, meaning they differ in amplitudes. We'll see that. Both of them, though, require the existence of a resting membrane potential and the presence of, whoops, hey, I figured it out quickly. Clicked on something. And the specific ion channels need to be present there. So somebody actually took a probe and they placed it in individual membranes. Actually, Dr. Gaffin over there, I used to crack on this and say, there's somebody out there doing this. I'll never meet him. I met him because he's done it. I'm like, I need to get him to come in and give a talk on it, but it's not that. I told him it's not really that interesting. I just like to point it out that they're down there microscopically figuring out the difference in voltages between the inside and outside of the cell. And they realize that when you depolarize the membrane, that changes. That's the voltage in the body. Right? We got to get nomenclature here and say, well, potential. Potential is the potential energy for electrical current. Remember, when we look at magnets, positive charges attract negative charges. Take a negative-sided magnet, place it towards the positive side, and they will come together. If you put the two positives towards each other, it will push apart. They repel each other. So if we take opposite charges, have you ever taken a magnet and you take opposite charges, positive and negative, and magnets together, it's hard to pull it apart, right? A little hard. You pull it apart. If you ever had magnets big enough or got them close enough, you'll feel they're trying to pull in, right? They're trying to pull together. Well, you can actually measure that energy, right? That is a form of force or energy, potential energy. Right? And if you wanted to measure that, they have in volts. The difference is in power lines and things like that, they're using a flow of electrons. In the body, when we say current or flow of energy in the body, we mean ions. Ions are different than electrons. Ions are things like calcium, potassium. I listed a few, but we could say any ion that has a charge, right, can make a difference in the body's current flow. But we're really specific to whether it's going through this membrane. So in order to depolarize a membrane, you have to change, y'all talked about this in cardio a little bit, right? You have to change the membrane. Did y'all go over like resting membrane potential, right, threshold? Okay, good. That's the same thing we're going over here, is you got to change the potential. Y'all save me a lot of talking like this. We're going to keep drilling this down. So the way that we're going to change the potential in a membrane is to have ion channels. Meaning we're electrically excitable. Meaning we can open ion channels for specific ions and allow them to cross the plasma limit, and that will change the difference in the charges across that membrane. Right? So they can basically use what's called an electrochemical gradient. Electrochemical, because if you look at sodium, it has a charge. Right? So it's a chemical that has a charge on it. So any movement is actually an electrochemical gradient, and you're going to move from an area of a different charge, positive to negative, negative to positive, and we're still using our concentration gradients, area of higher concentration to lower concentration. So anytime we can get those ions to flow, we can change the membrane potential. We're going to need to. But what's going to control that is going all the way back to our integral membrane proteins that are ion channels. There are many different types. We're expanding now. there are many different types of ion channels. So before we even get into it, you're going to start thinking about voltage, sodium voltage gates, that kind of thing. How did sodium get into the cell? I want you to remember this up front. There are many different types of ion channels. So there are voltage-gated sodium channels, there are leakage channels for sodium, there are receptor-gated channels for sodium. There are many ways sodium, for all ions, but for sodium specifically here, to go in and out. So the gate's just an integral protein that allows an ion in or out of that membrane or out of that cell. So we're going to look at these different types of channels. The first one, you have leakage channels. They're not considered gated. Right? You have more leakage channels for potassium than you do for sodium, which means that the resting membrane is more permeable to potassium than it is sodium. All right. Leakage channels allow sodium to leak into the cell, potassium to leak out. But we already know that in general, on a cell membrane, sodium's always higher outside the cell, potassium's higher inside. And so what that says is, before we get into action potentials, sodium's kind of leaking in, potassium's leaking out. And that always, in other words, the cell is adjusting its charges to maintain that resting membrane. Right? It's sitting there doing that. Right? So that would use something like a leakage channel. A ligand-gated channel, right, is a chemical, and it's looking for a ligand, a molecule, right, like acetylcholine. So ligand-gated channels are going to bind that receptor molecule, and when that happens, that will open this channel so that, we'll just say it can go in or out. We'll open a channel for that. Let's give an example we already know. Remember on the motor end plate of skeletal muscles, we have acetylcholine receptors. And acetylcholine came along and binded with those and opened it up. And what did it do when it opened it up? Allowed sodium to come in. That's a ligand-gated sodium channel. So when we look at our different types, that's just another way. So an acetylcholine receptor is really just a ligand channel. Sorry, ligand-gated channel. Okay, mechanically gated channels are going to be push-pull. Right? Mechanical stimuli, things that can push tension on, you put tension on the plasma membrane, sometimes that can open some channels. We don't spend a whole lot of time talking about mechanically gated channels other than that they exist, but there are. You talk about different pressures on membranes and things, you can change certain aspects. A lot of the time you talk about voltage-gated channels though. Right? Voltage-gated channels are very different than leakage channels, ligand channels, mechanically gated channels. Voltage gates are going to open in response to a change in voltage. I know that sounded funny, but that's where threshold and resting membrane potentials come in. That's what I'm going to try to explain to you. So here's a voltage-gated or potassium channel. And so we need this gate to open. Okay. At negative 70 millivolts, that gate will be closed. We'll talk more about numbers later. That will be closed. If you depolarize that membrane to below negative 55, and now it's at negative 50, the gate will open and allow things to come out. Now I put a note in there that the negative 50 doesn't result from potassium moving out, rather that sodium's moving in. So this is a key thing here is, before that voltage gate opened, we said we're just using random numbers right now, we were at negative 70. And when we got to negative 50, we dropped below threshold. If y'all from cardio, right? You went below threshold, now you get this spike on the graph, right? The way we got here was not using voltage gates. How did we get from negative 70 to negative? Ligand gated channels and leakage channels. But for a big part of it, it's ligand gated channels. So if you're tracking, we're going to talk about this even more, but if I open enough ligand gated sodium channels, such as in a motor implate of a muscle, what will I do to that muscle? I will depolarize the membrane. Right? I got to open up enough of those. But what I'm trying to say is, you have to open up enough ligand gated channels to hit negative 55 so that you get full opening of the voltage gates. I'm going to go over that again if you're not getting it. But, and I just put down here the ligand gated channels to tie in with that. So the understanding for this comes with resting membrane potential. In other words, think of a cell that we're not actively stimulating, and we said it wants to always balance its charges. Even though they're unequal, they're balanced, right? The charges are unequal, but it maintains that. What it's maintaining is the resting membrane potential, the voltage difference across the membrane. In that case, they say that membrane is polarized. So we look at these membranes and say, well, what's the potential inside of the membrane relative to the outside? And the resting membrane potentials in cells for here and forever during IPAP areas is going to be negative 70 millivolts. So that's a number you'd want to know, because negative 70 millivolts is resting membrane potential. Membrane is now polarized. The way we're going to set this up, how do we establish resting membrane potential? I said it's because you have an unequal distribution of ions, and the fact is that sodium and chloride are in higher concentration outside the cell. And when you look at potassium and a bunch of other anions, negative ions, they're higher inside of the cell. When we look at the permeability of the resting membrane, it's a lot more permeable, 50 to 100 times more permeable to potassium than it is to sodium. When you look at chloride, it's between that potassium, sodium, and then the membrane is nearly impermeable to all the negative charges. Okay, so let's break this down real quick. And just think of the cell. Sodium's higher outside, potassium's higher inside. Sodium's leaking in slower than the potassium's leaking out. Let's just picture, two sodiums are leaking in all the time and 3 potassiums are leaking out. And they're both positive. So you would think if sodium's leaking in, potassium's leaking out, that it would eventually equal itself out. It doesn't, because of the fact that chloride can come in very slowly also, but there are negative ions inside of that cell that really can't get out. So the inside generally stays more negative. That kind of makes sense? That plus you're losing more potassium than you are sodium coming in. So it's always maintaining that negative balance inside. So what's going to start this, or it's always going on, but we got to look at it while you're starting, is potassium diffuses down its concentration gradient out of the cell. The negative ions inside, intracellular ions that are negative, are left in there. So the interior of that cell becomes more negative, the exterior becomes more positive, because we put more potassium out there too, right? So that's a positive ion. So at some point, these will balance out to where you continue to have that equalization. But sodium's coming in much slower, right? Because it's less permeable, the membrane's less permeable, and like I said, some of the chloride can also diffuse into the cell, making that interior more negative. All of this is what I stood up over here right before this and said, just in the verbiage of things. So the net results resting membrane potential, which will always be for us negative 7. So that's where we start. But we're going to change that membrane potential. need to change it. We're going to start by using these lagging gates. So think of leakage channels for sodium, potassium. That's just going on all the time. That's the ebb and flow of a normal cell that we're not trying to change the membrane potential. It's maintaining its resting membrane potential all the time. And then along come lagging gates. Right? Something causes the lagging gate to open. Right? So they produce what's called graded potentials in response to a stimulus. That's the same as saying acetylcholine binded to a receptor and open that gate. That is a stimulus. The stimulus in that case would have been that molecule. Graded means that the size of the change in the membrane potential varies. Right? So how strong the stimulus is. How many acetylcholine channels did you open? Did you open 1 or you opened 50? Right? I hope y'all are tracking with me today. It doesn't look like it, but I'm trying not to stop. Is if you open 1 lagging gated sodium channel, you'll let some sodium in. May not be enough to depolarize that membrane, right? To reach resting or to reach threshold. But if you open many acetylcholine receptor lagging gates, you're more likely to reach threshold. That's why it's not called all or none. Because it's graded. It's a local effect. So what happens with graded potentials is, if we look at -70 being resting membrane potential, and in that area, because it's -70, that's called polarized. Well, what if the membrane becomes more polarized? Or it goes further negative? Like it drops down to -75. Now you're not just polarized, you're hyperpolarized. If you want to depolarize it, if this membrane potential goes from -70 to -60, now you've depolarized the membrane. It's more positive. Even though it's negative, is -60 more positive than -70? Yes. Go back to your graph charts like in elementary school, right? You got 0, all your positives, all your negatives, right? If I'm on the negative side of the chart at -10 and I go to -5, I did go more positive. So that's called depolarizing. Right? You're making it less negative. All right. Action potentials are all or none. So once you start an action potential, it will go down the length of that neuron's axon completely to the end. And initiate probably some change in whatever it's connected to, muscle gland, another nerve. When you look at action potentials, they really concern voltage gated channels. Everything led up to this point where we get the voltage gated channels. Because now we need to reach thresholds. So some stimulus comes along and causes your membrane to depolarize enough to reach -55. It's another key number you gotta know. -55 is threshold. Right? And then we will repolarize it after we depolarize it. We'll close those. Okay. Let's look at this and then here's what's happening. This is the last thing we're going to kind of look at. I'm going to draw one picture and show you this. I'm going to talk through. Actually, I want to draw one thing and then we'll close. Here is, let's put a bicep out here. I'm going to try and, I don't think y'all really understand, maybe do the difference that we're trying to make with graded potentials versus all or none. So this is going to be our bicep. I know it looks funny. Bicep. And then Does that look like a neuron deal? Dendrites here? Okay, thank you. There is a neuron that's going to a muscle. Alright, now this is a very rudimentary example. Graded potentials, we're going to talk about this tomorrow, but I think we're losing it because I haven't said this part yet. Is if we look at neurons, remember multipolar, different types of pseudo-unipolar, all those different types of neurons, neurons do talk to other neurons. These are all axons off these neurons. Right. We're going to discuss this in full tomorrow, but these neurons can produce graded potentials, and they're called excitatory or inhibitory. So if this neuron produced an excitatory, these are graded, like it excites it 3 times, but one of them is inhibiting it. So what do we mean by exciting it? Exciting it means we're going to start depolarizing it. Right? So if I had 3 neurons that are trying to depolarize it, and one that is trying to inhibit it or repolarize it, hyperpolarize it, they're going to probably be enough. So you have enough graded potentials here to make this neuron reach threshold. And once you do that, it will send a signal all the way down the axon to activate that. It's not as easy as that. But that's the difference between a graded potential and all or none. And that leads you to, the reason I just drew this, I know we're already there, sorry. Let's say this, no we don't. Here's -70. Right? That's resting membrane potential. You have a stimulus that came along. That stimulus takes you to here. You see the green where it starts? Then you get this big spike. That big spike is because sodium is flowing into that cell. It's depolarizing that membrane completely. So I'm going to say this and then we'll be done and I'll start here tomorrow and redo it. Here's -55. That's threshold. So at threshold, sodium voltage gated channels open and allow sodium to just flood into the cell, completely depolarize the membrane. But what I wanted to finish with is you had to get there. And if y'all got any of what I've been saying this hour, you could answer this. Here's the stimulus. 2 questions. What would be a stimulus that might start getting you there? Ligand-gated channels, right? Acetylcholine receptors open ligand-gated channels. So if I open if depolarization involves sodium, if I start to open ligand or mechanically gated channels and start allowing some sodium in there, that would take me from -70 to maybe -60. Okay? That would be a graded potential. But what if I didn't have any more sodium coming in? I would go right back to resting potential because the cell will establish its resting. You have to reach threshold. The key I was trying to make is this would be a ligand-gated channels opening. But if you open enough of those and you get to this spot here, at this exact moment, once you reach -55, voltage-gated sodium channels will open. They allow mass influx of sodium. We'll start there and repeat that tomorrow. But if you're following kind of with that, that gives you now a better visual picture of graded potential. It's graded. How large of a change can we make versus all or none? Because once this happens, you're off to the races. Right? It's exactly how you should be entering the highway on the acceleration lane. Y'all have a good day. Sorry, I took some of y'all's time. Too much. I'll tell Rosario y'all start saying that. How's that? How you doing?